In Lesson 3, we will cover the host implementation of the 802.11 application framework. Specifically, we will go over an overview of the host code, discuss some programming basics on the host, go into details on the host implementation, and then discuss MAC and physical layer separation event tracing. Section A, Host Code Overview. In this, we will do an overview of the front panel and the block diagram of the host code. This is what the front panel of the host code on the application framework looks like. This front panel will allow you to configure settings in the application framework using various controls and drop-down menus, and will also allow you to view data that is received. In other words, throughput or constellation or power spectrum. Specifically, the Basic tab has all the basic things that you need to get started. If you click over to the Advanced tab, you will see more sophisticated controls and indicators. Finally, the Events tab enables you to trace PHI-SAP primitives according to the 802.11 standard. On this tab, you have different events that you can choose to track or not track, so you can see the information that is valuable for you. If you hit the diagram button at the top, you can then see the source code of your host code. The block diagram is organized into three main components. The first is the initialization. The second is then the main part of your code. This has several loops running in parallel and leverages the ability that LabVIEW has to take each of these loops and automatically use them on different cores of your multi-core PC. Finally is the cleanup section of the code, so that your code shuts down gracefully. To go over each of these loops, the first loop is a configuration loop. This configures the RF, the baseband, and some of the statistics calculations. The next is the transmission loop, which handles taking data from the host down to the FPGA. The next is the reception loop, which handles receiving data from the FPGA. The next loop is the UDP send and receive loop that allows us to send data to and receive data from a UDP data source running on the PC. Then there are two loops for updating plots, one which updates plots that only need to be updated slowly, and one that updates plots much faster. In Section B, we will cover some basics of doing G programming on the host. G-code is a graphical LabVIEW programming language. It can be run directly by just pressing the Run button. A LabVIEW VI can run both top levels and sub-VIs directly. To create a new VI, you just go to File, New, VI, or hit the plus button at the top and add a new VI. G-code on the host includes a whole host of debugging features such as breakpoints and probes, and also allows you to slow down the code and see the data traveling through the wires through something called highlight execution. G-code supports floating point, fixed point, and integer numeric data types. It supports enumerations, booleans, and strings. You can also have arrays of variable sizes, multiple dimensions, containing any of the above types. And you can also have clusters, which are the equivalent of structs, which can contain any combination of the above types. Your top-level code in G is going to be called a VI. This VI is going to have controls and indicators on the front panel and are used to enter and display data, as we saw with the application framework. Within your top-level VI, there will be different sub-VIs or sub-functions. With sub-VIs, the controls and indicators are typically connected to the connector pane of the block to allow you to specifically specify the inputs and outputs. You can use controls and indicators on sub-VIs on the front panel, but typically this is just for debugging only. There are two different ways to transfer data between parallel processes using your host code. The first option is what is called a duplicate terminal. For these, you can right-click on a control and choose Duplicate Terminal. This allows you to implement a one-writer, multiple-reader type of architecture. These are very quick to do. However, they only store the latest data, so data cannot be streamed with duplicate terminals. If you want to stream data instead, use queues. There's a queue palette in programming flow at the top, and then synchronization, and then queues. queues are used to stream data losslessly between tasks running in parallel on the host. When you set up a queue system, you need to use an obtain queue function first, and then a release queue function afterwards, so you can properly manage the data. This is what the use of queues looks like in LabVIEW on the host at the most simple level. First, we have an obtain queue block to implement our queue. Then we have two loops running in parallel with each other. On the top, we have a write queue, which writes the element to write to the queue, and at the bottom, we read that element. If, for example, the loop at the top is running much faster than the loop at the bottom, then that data will get buffered, and the bottom loop will read all of that data losslessly. This host architecture is what we call a producer-consumer architecture on the host, and enables you to easily leverage the multi-core processors to have different functionality running in parallel on your host. All right, now go through an activity. Implement the queue example as shown on the previous slide, and play around with transmitting data between different loops running on your host. Section C, Host Implementation Details. As mentioned previously, the block diagram on the host in the 802.11 application framework is divided into three main parts: initialization, the main chunk, and cleanup. First, we will go over the initialization code. In the initialization code, four main things happen. The first part is we download the bit file to the FPGA and actually start the FPGA code. Remember, the FPGA is running most of the physical layer, and therefore it is really important that we do this. The next part is to initialize the USRP. The next is to actually start our DMA FIFOs so that we can stream data to and from the FPGA. And then finally, we start all the host queues so that we can pass data between all of our loops that are running on the host, like seen on the previous slides. Now let's go over the main part of the code. As these are all loops, these will all run in parallel continuously and contain the meat of the functionality of the application framework on the host. Let's review what these all do. First, let's look at the session cluster. The terminal session is duplicated in all of the processing loops. This is one of those duplicate terminals we discussed previously. The session cluster contains the reference to the FPGA interface, the reference to the UDP RX socket, and host queue references. In 802.11 unbundle session, we can access all the different references easily in the code. Clusters, which are covered in some of the core LabVIEW training, allow you to easily pass around groups of related data. So in this case, we include all our main references for data communication, whether it is to and from the FPGA, between our different loops, or from the host code to our UDP source. This is the top part of the configuration loop in the application framework host code. There are three main blocks to care about here. The first is called configure static parameters, and this configures parameters such as the device MAC address, the operation mode of the application framework, and the primary subband. The next two blocks are the configure TXRF and configure RXRF. These configure the RF frontends. These specifically look at things like the transmit and receive ports for the USRPs, the frequency that we're transmitting at, and the power level that we're transmitting at. Within the configuration loop is also the AGC part of the loop. This loop writes new gain values to the FPGA. Note that the actual AGC code itself is implemented in the FPGA code. Now let's look at the TX transmission loop. The first block reads off a queue to read the data to be transmitted. The second block converts the MCS to format and bandwidth. The third block selects the MAC address. And the fourth block sends the packet, including configuration and data, down to the FPGA. We will look specifically at the send TX ICP block on the next slide. This is what the code in the TX transmission block 802.11 send TX ICP.gvi looks like. There are four main parts to this block, and these are important to understand so you can see how data gets sent down to the FPGA. The first section is this control here, which prepends the packet size. The second part prepends the configuration. The third part actually builds the payload data. And the fourth part writes this packet, which is the configuration and the data, to the FPGA. So here you can see through steps 1 through 3, we just build our packet, and then finally we send that packet down to the FPGA. Pretty simple. Now let's look at the RX reception loop on the FPGA. Specifically, we will look at the receive RX ICP block, which reads the received packet from the FPGA. There's a lot going on in this block, but we can break it down into 4 simple parts. The first part are read DMA FIFO blocks that stream data from the FPGA. The second part appends this data to existing data using essentially array manipulation. The third chunk of code in the box removes the ICP header. And then the fourth chunk of code writes the data to the received queue and writes the packet length to the received throughput queue. This data can now be accessed in other loops on the host that are running in parallel to this reception loop. Next, let's move on to look at the UDP send and receive loop. There's really 2 main chunks of code to care about here. The first is the module to read data from the UDP port and write it to the send queue. In other words, if we are trying to stream video over the air, this block will allow us to read the video from a UDP port and send that down to the FPGA. The second block does the opposite. It reads data from the received queue, which, if you recall, gets filled by the RX loop, and transmit that via UDP so that a UDP sync can actually read that data. Our final 2 loops of main code on the host are the slow and the fast update plots and indicators loop. The first loop is the slow loop, which runs once every 250 milliseconds, and this will update the RX constellation, the RX power spectrum, our channel estimation, and the TX power spectrum. The fast loop will run once every 100 milliseconds, and this will update our throughput constellation and our block error rate constellation, which we want to keep up to date a lot faster. So we reviewed the details of the initialization and the main chunk of code in the 802.11 application framework. Now let's briefly review the cleanup section of the code. The main thing that we care about here is that we look and manage all our errors from the various loops in case there were errors that occurred, and we also close the FPGA target so that we can shut down our physical layer. This ensures that when we start our code next, everything starts in a clean and known state and we don't have any weird transient properties in our behavior. In Section D, we will cover the MAC-PHY separation event tracing. Event tracing is available for PHY SAP primitives, which are MAC-PHY requests and indicators. These can be activated on the host in the Events tab, and you'll notice that there are various booleans on the right so that you can choose which events you want to track and which events you do not want to track. An example for the sequential order of PHY service primitives for regular transmission and reception is shown on the slide. For version 2.0 and 2.0.1 of the application framework, only primitives that are essentially needed are implemented. An example for a primitive that is not implemented is the PHY txstart.cnf, which could indicate an error event from the PHY to the MAC after a PHY txstart.request is received by the PHY layer. This is an example flow of events on the transmitter. For the event MAC TX status indicator, the flag is TX after backoff pending, which means MAC transmission is pending. The host has provided data to be transmitted. For the event PHY TX start, this means that the PHY transmission has started. Then on the MAC TX status indicator, the flag TX after backoff active is 1, means that the MAC transmission is active. Then again on MAC TX status indicator, TX after backoff active 1, FCS after done 1. And then on MAC TX status indicator, TX after backoff active 1, And then finally, TX phi end indicator means the phi transmission is finished, so then MAC TX status indicator indicates that the MAC transmission has finished. This is then the example flow of events on the receiver. For the event phi CCA timing indicator, the flag energy detection busy is 1 means that the energy threshold has been met, so some signal has been detected. Again, for the event phi CCA timing indicator, energy detection busy 1, signal detection busy 1 means that the energy threshold is met, and an 802.11 preamble has been detected, so the receiver is synced. Then, for phi RX start indicator, the flags format, bandwidth, and MCS mean that the signal field was decoded correctly and the data field will be decoded next. Then, for phi CCA timing indicator, signal detection busy 1, this means that an 802.11 preamble has again been detected and the receiver is again synced. Phi RX end indicator, timing valid 1, timing value, means that decoding was finished and successful. Then for the event MAC channel state indicator, frame timing use diffs 1 means we will align in the next frame using diffs. And finally, phi CCA timing indicator, energy detection busy is 0, means that the energy threshold has not been met, so no signal is detected. So this again is the example of event tracing in the Events tab in the application framework on the front panel. Some notes here on data source. UDP is a packet sent when data is received via UDP. PN data is random data that is sent at a constant rate. And manual is random data that is sent at a click on trigger TX. In exercise 3.1, we will look more into event tracing. For this exercise, open the 802.11 project and the top-level host VI. Run the VI, and then change the following settings. On the Basic tab, leave the frequency at 2.437 GHz. On the Advanced tab, set data source to manual. And on the Events tab, ensure that all events are enabled. Set the switch for station to on while you are still on the Events tab. And what do you see? Set the frequency on the Basic tab to 2 GHz. What do you see? What do you see in the Events tab when you press Trigger TX on the Debug tab?